हा आणि स्क्रीनशॉट सुद्धा घ्याल काय? स्क्रीनशॉट सुद्धा घ्याल म्हटलं, मी जरा मोबाईलवरनं झालेलं जॉईन, त्यामुळे स्क्रीनशॉट नाही घेता येणार मला. येस सर प्लीज.
Yeah, thank you. So good morning everyone and welcome back to the second day of the session on quantum computing. We will start off where we left yesterday. If you think you understand quantum mechanics, you really don't understand quantum mechanics. That's where we left yesterday. And to recap what we did yesterday, we went through the Moore's law, which stated that transistors now have reached their maximum limits, whether it is in terms of the density on the chip, or whether it is the size, which has come down to 7 nanometers. We also saw that there are certain problems that are unsolvable by classical computing algorithms, or it might take more than the age of the universe to solve a simple problem because of the exponential nature of the problem, which is 2 raised to n. The weirdness that we saw in quantum computing, so two weirdness that we went through yesterday was superposition, having 0 and 1 at the same time, and interference, the dual particle behavior as a particle and as a wave. Lastly, we saw the qubits, which forms the basis of computing in quantum computer, and their scaling power, how a few qubits can store exabyte of data vis-a-vis classical bits. Today, we are going to look at the third weirdness characteristic of quantum mechanics, which again plays a very important role in quantum computing. And this phenomena is called entanglement. So what is entanglement? Basically, if you look at it from quantum angle, it is the ability of these quantum systems that we are talking about to have correlation between states within a superposition. So when we were saying that one qubit can be in 0, 1, or 0 and 1 together, if we talk about 2 qubits or if we talk about 3 qubits, then entanglement says that if you try to measure 1 qubit, it will automatically have an effect on the other qubits also. This is as confusing as it may sound. It's not that difficult to understand. So we can entangle the 2 qubits such that measurement of 1 qubit will always be correlated to the measurement of the other qubit. How do we understand that? Now I've tried to make a small presentation, and the goal is to go through this, understanding how entanglement works in quantum mechanics. For that, let us recall that any classical information can be put in terms of indivisible units called bits of information in classical computing. So we could store any information in classical bits, and we know about it. Similarly, and we might envision a bit as an object, like let's say a ball, which can be either of 2 colors, like red or green. And because we value our bits, we store them sometimes. I can put a bit inside a box and then later on close the box. And once I put it out again or open the box again, the red one will come out as red and the green one will come out as green. Well, by quantum bits, the information carried by a quantum system and for quantum information as well, it can also be expressed in terms of indivisible units, what we could call a quantum bit or qubit. And for many purposes, we can envision a qubit as again an object that is stored inside a box, but where now it is possible to open the box in two complementary states through two doors, which you see are labeled 1 and 2. So we can put a color ball inside a box through either door number 1 or door number 2, and then later on, so we close the box, and later on when we open the box, if we open that same door again, and the color ball that we put in comes out again, so we say that we recover a bit just as though it were a classical bit, right? It is similar to how the classical bit behaves. But on the other hand, what we can do is we can put information in a qubit through door number 1, and then later on open door number 2 to measure the qubit. Now here is where the qubit behavior differs. What comes out is completely random and unpredictable. It has a probability of 50% of being red and 50% of being green. So if we are going to read information in a quantum system, we have to go about it in the right way. If we read it the wrong way, we'll actually spoil or destroy the information. And one consequence of that we can appreciate if we think about what it would mean to copy quantum information. Let's say I have something called a quantum copier, just like a Xerox machine. So if I have that, it would mean that if I happen to have put information in a qubit through door number 1, and I could copy the box, and then later, if I were to open that second box, whatever was there put through door number 1 or door number 2 should come out of respective doors. Later on, if I were to open door number 1 or door number 2, we should see the duplicate colored ball that I would put come out of both the boxes. But the mechanics here says that nothing of this sort exists. Why would that be there? The reason is actually quantum mechanics itself doesn't allow such a behavior or a device to exist because of the randomness of this probability that we use. We can't copy unknown quantum states because at every point in time, until we open the box, the qubit is in unknown state. We don't know whether it is 0, 1 or any combination of 0 and 1. So it is in a superposition state. Now in a superposition state, we cannot copy a quantum bit. And the reason is that the copier, in order to copy the color of the ball that's inside the box, has to look inside the box. It has to open the box in some way, and it might guess correctly that the door we used, and then it would be able to copy the information without any problem. But if it takes a wrong guess, let's say we put the bit from door number 1, and quantum copier thinks or takes a probable guess that we might have put it through door number 2, it opens the wrong door and then it would damage the information, and it would not be possible after that to make a copy. So although today we claim that we are able to clone a sheep, what is surprising is that we cannot clone a qubit, and that is by its intrinsic nature. And the reason we are describing qubits in this abstract way is on purpose, because it's useful to use that level of abstraction for the purpose of thinking about qubits. But any qubit in the physical world will have some physical realization. And as we go ahead in this course, we will see what it means to be in these different states, and the property that it cannot be copied. So let's take an example of a single photon or particle of light which has a single photon, and it has an electrical field. We could imagine that the electrical field is oriented either horizontally or vertically, as shown in the diagram on the left part, corresponding to the two colored boxes that we were seeing, red and green. When our two colored when we look through the box, we look into the box through door number 1. But on the other hand, we could consider the electrical field oriented along these 45-degree rotated axis that you look on the right side of the figure, and measuring the electrical field in that way corresponds to opening door number 2 for the qubit. Now, what we really want to see here is the important way in which quantum information is different from classical information. We are going to have to consider systems of more than one qubit. So let's suppose we have 2 qubits, and they are far apart from each other. So let's say there is 1 qubit which we have on Earth, and one of the qubits my friend has on Mars. They're totally on 2 different planets. As we know that a quantum subatomic particle not only can be in 2 states, but it can also be in 2 places at the same time. So let's consider this qubit on Earth and the qubit on Mars, and somehow they are correlated. Now, sometimes at some point in time, some time ago, when these qubits were made on Earth, they were prepared in a special state with some unusual properties. Namely, I can open my box through either door number 1 or door number 2, and when I do so, what I find is a random value, 50% probability of being red and 50% probability of being green. And the same thing is true for my friend who is in Mars. So means that neither one of us, by opening his box, actually is gaining no information. It's just something random that's coming out. All we are doing is generating a random bit. And that's kind of peculiar, because with 2 boxes, we should be able to store 2 bits of information. Where is that information hidden? Why is it coming out random? The answer in this case is that all the information is actually encoded in the correlation between what happens when you open a box on Earth and when you open a box on Mars. Because out of the special state that we prepared, if my friend and I both open door number 1, I might see a green ball or a red ball. But whatever I see, my friend on Mars is guaranteed to see the same as well. If we both open door number 2 again. What I find could be a red or green, but if my friend opens the same door in Mars, he'll see the same color that I do now. So there are really 4 perfectly distinguishable ways in which a box on Earth could be correlated with the box on Mars, because we could see either the same color or different colors when we open door number 1 or door number 2. And we have chosen one of those 4 possible ways. That's 2 bits of information stored in the 2 boxes. But what's unusual in this case is that the information is completely inaccessible locally. It's entirely stored in the correlations between these 2 distant boxes, separated through the galaxy, and that property of quantum information, that it can be stored non-locally and still be locally inaccessible, that's what we call quantum entanglement. And it's really essential way in which quantum information is different from a classical information. Now look at correlation themselves. Correlation themselves are not such an unusual thing. We encounter them all the time in our daily lives. For example, let's take an example of socks. So they are always of the same color, and that means that if you look at one of my feet, then you already know what socks you will expect to see on the other foot. And it's kind of similar with these quantum boxes. If I want to know what my friend is going to see on Mars, all I need to do is what my friend sees on Mars, if let's say he opens door number 1, all I want to do is open door number 1 on Earth. And I can find out. And on the other hand, if I want to know what my friend will find when he opens door number 2 on Mars, I just have to open door number 2 on Earth, and I find out what he'll see. So you might think that these boxes are just like soxes, and there's nothing new here. But that's not correct, because the boxes are really not like soxes. The essential difference is there's just one way to look at my socks. But there are these 2 complementary ways of looking at the boxes, and that means the correlation of boxes are richer and lot more interesting than the correlations among classical systems like socks. Now, this idea of quantum entanglement was first explicitly described in a paper by Einstein, where and 2 collaborators along with him in 1935, where he said he found out that quantum entanglement, this phenomena of quantum entanglement, where you correlate 2 qubits who are distant apart, but they still open up in the same state, he really found it to be very, very disturbing. And it seemed so unsettling as to indicate that something was really missing from our current understanding of the quantum description at that time of the nature. And that paper elicited some interesting responses, including one that was particularly perceptive by Schrödinger. We already saw Schrödinger has his experiment of the cat, dead or live cat. So Schrödinger wrote a few months later characterizing that he characterized the situation in such a way that the best possible knowledge of a whole does not necessarily include the best possible knowledge of its parts. So what Schrodinger meant was that even if we have the most believed description of this pair of qubits that nature will allow, we are still completely helpless to predict what will happen when I open either door, door number 1 or door number 2 on my qubit. And it was Schrodinger who suggested using the word entanglement for this particular quantum of correlation. And he also added that it is rather discomforting that the theory should allow a system to be steered into one or the other type of state at the experimenter's mercy, in spite of having no access to it. And what Schrodinger meant was that it's really up to me to decide here on earth whether I will open door number 1 and therefore be able to predict what my friend will see when he opens door number 1 on Mars, or I open door number 2 and that will decide what my friend on Mars will see when he opens door number 2, even though these boxes are far apart from one another. Now, Schrodinger understood that these correlations, though peculiar, do not allow us to send a message from Earth to Mars. There is no way that you are sending any message. No matter what I do, my friend, when he opens either door number 1 or 2, just sees a random bit, and he doesn't learn anything about what I have done here on Mars, and therefore receives no message from me. Now, the theory of quantum entanglement did not advance very much for nearly 30 years after that. So it was only around 1960s when we saw something more happening, some action happening on this. For nearly 30 years and until in the mid 60s, starting with John Bell, who again started to focus on entanglement theory. And he started thinking about entanglement in a rather different way. So entanglement is not just something mysterious and peculiar. It can be a resource, something that we can use to do things that wouldn't otherwise be possible. Just like we saw superposition and interference, their weirdness can be used to do something which is just not possible by classical computers. Similarly, Bell started to think that can we do certain things that wouldn't otherwise be possible. So he went on to explain the details. He said, I'll try to give you, let's imagine 2 players. So he put a small experiment where he said that imagine we have 2 players. We all must have seen those video games today's kids play on mobile, where 4 people are playing together. The friends are sitting all in different places of the world. You know, one is sitting in USA, one is sitting in somewhere in India, in North India, someone is from Bangalore, and they are playing this game together. The only difference is that in that game, they are able to communicate with each other. But when we are talking about quantum entanglement, you are not able to communicate with each other, but you are still playing a game together. So imagine that we had 2 players, say Alice and Bob, who are playing a cooperative game. That means both players are on the same side. They are both trying to win. And this game has the following structure. Alice and Bob each receive inputs, and they are then, based on their inputs, they have to produce outputs that are correlated in a certain way that depends on the inputs they receive. But under rules of the game, Alice and Bob can communicate in the middle of the game So Alice has to produce, they cannot communicate in the middle of the game. So Alice has to first produce her output before knowing what Bob's input was. And Bob has to produce his output without knowing what Alice's input was. Now, it may be that they have correlated bits distributed before the game began. They don't know about it, which they can use for a particular game. It turns out if they play the best possible strategy, they can win with at best a success probability of 75% if we average uniformly over the inputs they could have perceived. But let us now consider a quantum version of the same game in which before the game began, correlated qubits were distributed, just like we had correlated boxes, one on Earth and one on Mars. If we were to distribute correlated qubits to Alice and Bob before the game started, and they were entangled qubits, now it is possible for them to play a better strategy with entangled qubits or quantum strategy, which will enable them to win the game with a higher probability of success, let's say over 85% instead of 75%, which we saw earlier. And so the entanglement is useful for something. Well, at least it allows you to win the game with a higher probability. Experimental physicists, they have played this game as a model, and they have won with more than 75% probability that Bell pointed out is possible in a quantum world, but not in a classical world. So these quantum correlations really do seem to be part of the way nature behaves. Now, Einstein had derived quantum entanglement, and he called it the spooky at a distance. Spooky because nobody understands how that is working, but we know that it works. You know, something we all love about science is that it doesn't matter what anyone's opinion is. Even if it is Einstein's opinion, it really doesn't matter. Nature is the way she's revealed to be in experiments. So what you and I think or what Einstein thinks doesn't really matter. It's the nature, and whatever way nature reveals itself in the experiments. And if the experiments tells us that that super strong correlations are part of nature's design, then so be it. We have to learn to accept it and love the nature as she is. So boxes are really not like soxes. We come to that conclusion. With boxes, well, we can win a game, as you see, with the higher probability of success, 85% instead of 75%. Is this really such a big deal? We are talking so much about boxes and soxes and correlation between two qubits and how they are entangled. Is this really such a big deal? Well, in one way, yes, it really is a big deal. And why? This is a big deal, and to appreciate why it's a big deal, we really should consider systems with more parts than just two parts. One way of thinking about it is we can imagine a book, let's say a book which has 100 pages. Now, if this were an ordinary classical book that we would print on every page, and let's say it's a 100-page book, we can read 10 pages, and after reading 10 pages, we can with confidence say that now I know 10% of the content that is there in the book. But suppose it's a quantum book where each page is a quantum system in itself and the pages are highly entangled with one another. Well, then if you look at the pages one at a time, we just find some random gibberish with no information content there, because the information is actually encoded in the book, but we cannot perceive that information by looking at the pages one at a time. That's because the information isn't recorded in the individual pages. Hardly any of the information is recorded that way. It's almost entirely recorded in the correlation among the pages. And to read those correlations, we have to make a collective measurement on many of the pages at once. Well, we can think about it this way. Let's compare many classical bits with many qubits. Suppose it's 10 classical bits we've got. Okay. Now, let's say there is a colored ball in each of the box as well. Okay. So there are 2 to the power of 10, which is almost 1024 different ways that we can find the balls in those boxes. But for any one of them, we can describe it very precisely to tell each one of the 10 balls whether it is red or green. Suppose, on the other hand, we have 10 qubits. Well, now the things become different. Now we are having 10 qubits, and they're different because it's not correct to say that each ball is red or green. Rather, it has some probability of being red or green, and also there are complex correlations between what I see if I open door number 1 or door number 2 on one of the boxes as opposed to door number 1 or door number 2 on another box. So with just one typical highly entangled state of 10 qubits, if we wanted to completely describe those correlations, we'll have to write down a lot of numbers, more than 1,000 numbers in this case, just to represent 10 qubits. Now, as the number of qubits increase, so let's say we have 20 qubits, well, now we need about 1 million numbers to describe all the ways these qubits are correlated in some highly entangled state, or 1 billion numbers, let's say, for 30 qubits. And when the number of qubits is still rather modest, just a few hundred or so, if we had some typical highly entangled state of, let's say, 300 qubits, and we wanted to write down a complete description using classical bits of all the ways those qubits are correlated with one another, we would have to write down more numbers than the number of atoms in the visible universe. And we saw that yesterday that it's clearly not possible because of the power of 2 raised to n. It is not possible to write such a description down in terms of bits. And that property of quantum information, that we can't hope to express it in any precise way in terms of ordinary classical information, was very intriguing to our friend Richard Feynman. We remember Richard Feynman, who says that if you think you understand quantum mechanics, you really don't. So, and it led him to make the suggestion in the 80s now that perhaps if we build a computer, a quantum computer that processes qubit instead of bit, then maybe we'd be able to perform tasks that just wouldn't be possible with ordinary digital computers. Now, his idea was that if we can't even write down in terms of classical bits the state of few hundred qubits, then if we process the qubits, shouldn't we be able to do something that can't ever be emulated by an ordinary digital or classical computer? While in the early 80s, when Feynman was thinking about these things, there was another guy, we spoke about him yesterday, Peter Shor. We know about Shor's algorithm, for prime numbers, and we will go through it today also. So there was this another guy, Peter Shor, who also was studying physics and not really advanced physics, but something intrigued him also. And what he started thinking that he actually made a rather amazing discovery, an example of a problem which seems to be hard for today's classical computer. If you know about it, is finding the prime factors of a large composite integer. So if you have a very large integer, and if I were to ask you to find prime factors, you see the other way around is very easy. Multiplying two prime factors to get a prime number is very easy. But if I give you a prime number and you have to find a prime factor for that, that requires a lot of steps. Now, what Shor discovered is that if we can build a quantum computer, then the factoring problem would actually be a very, very easy problem. It wouldn't be much harder to find prime factors than it is to multiply the numbers together and find their product. So when we heard about this discovery in the 90s, it was like, awe-striking. I mean, we understood what it meant, that the boundary between hard and easy problems, which means the problems that we can expect to solve someday with sufficiently advanced technology, and problems we can never hope to solve, that boundary is different than it otherwise would be, because this is a quantum world and not a classical world. So for example, about the hardest factoring problem that's been solved in finding the prime factors of 193-digit number, and it took several months for a network of hundreds of computers to solve that problem, collaborating together over the internet. And from what we know about how those algorithms scale using that hardware, we can estimate that if we want to find out a 500-digit number instead of a 193-digit number, if we want to find out prime factor of an integer which is of 500 digits, it would actually take longer than the age of the universe. So we don't expect to be able to factor a 500-digit number with digital technology in the foreseeable future. But suppose suppose it's not true yet, but we have a quantum computer which has the same clock speed, let's say 3 gigahertz or 2.2 gigahertz, same as that of any classical computing system, and it can perform the same number of elementary operations per second as the classical computer, then it would be able to factor the 193-digit number in 1/10 of a second. That's just 0.1 second. And the 500-digit number, it could find the factors in less than 2 seconds. Now, the vastly different scaling of the resources we need to solve the problem. As the problem size increases, if we use a quantum computer, The important thing, well, you might say, if does nobody care about factoring large numbers? Who cares? Well, actually, you will, when you go a little bit and do some research, you will see that many people do, and some people really, our lives are depending on these factoring of numbers, uh, because public key encryption, the crypto systems that we know about, the RSA keys that are in widespread use today to protect the privacy of all the transactions that we do over internet, that crypto system built by Ron, Addy, and Len, the RSA security, the public key and private key, which we all have must have studied in your BE courses. That crypto system is based on the difficulty of factoring and the difficulty of solving related number theoretic problems. The quantum computers will be able to easily solve. So perhaps some decades from now, when quantum computers are readily available, we will not be able to use the same method we use today to protect our privacy. Well, alternatives exist, but it's not yet clear exactly what will be the best path for protecting the information in the post quantum future, let's say. The really important thing that we learned from Shore is that if we look at the class of computational problems, there's an important distinction between the problems which are easy for classical computers and the problems that are easy for quantum computers. They are totally different set of problems. And the factoring problem seems to be one which is hard for a classical computer and easy for a quantum computer. And it's important as a research theme to address the question, what else lies in that intermediate regime? What other problems lie in those regimes that quantum computers can do and classical computers cannot? It's kind of frustrating though, because although a lot of theoretical work is being done on quantum algorithms, we can run those algorithms. There's no possible way of running those algorithms because we are still limited with the qubits that we have been able to manufacture in a quantum machine. Now, another very interesting problem, if you might know about or heard about, is the traveling salesman problem. In the traveling salesman problem, let's say there's a salesman who has to visit each city, starting, if there are two cities and he has to visit both the cities, he has two options. He can first go to city A and then to city B, or he can go to city B and then to city A. So we are talking about two factorial combinations. If he had three cities, then we are looking at 6 combinations, just like we saw yesterday, the power of factorials, power of n. Now, if we take that to 50 factorials, all the supercomputers packed together cannot solve it for the age of the universes combined together. That is the kind of computation that is needed because classical computer works in a serial fashion. Now, such kind of problems like the traveling salesman problem and this the factoring problem, these kind of problems are really what we call quantumly easy problems and classically difficult problems. There are many other problems of similar nature. If you go to Wikipedia and search for quantumly easy problems, you will find a list of things that only quantum, at least on theoretical basis, they know that only quantum will be able to solve. Now, if this is such an important thing, and if we know so much about it, what is it that it is taking so much time to build a quantum computer? Why just not go ahead with it, build a quantum computer and get ready with it? What's stopping us? Is this just a technology problem? Or could there be some issue which, as a matter of principle, will prevent us from ever operating large scale quantum computers that can solve these hard problems? And in particular, what we might worry about is the problem of errors. Quantum computing would be particularly susceptible to the damaging effects of noise. Physicists sometimes like to talk somewhat fancifully about a quantum superposition of the dead and live state of a cat, which we saw yesterday. But the noise gives rise to another terminology, which is called decoherence. So what is decoherence? We'll understand through this. It's how the noise of the environment affects or introduces error in quantum computing. Now, yesterday we looked at the Schrodinger's cat experiment, where the cat can be in dead or live state. And we never actually see in our everyday lives that sort of superposition that a cat is in both states of microscopically distinguishable states. And we understand why that's the case. It's because a real cat can't possibly be perfectly isolated from its environment or its surroundings. In theory, if you put it in a container and seal it, it is possible to isolate it from the environment, and that is why the superposition or entanglement is possible. But in the real world, it cannot be isolated from the surroundings, and the interactions with the environment, in effect, immediately measures the cat, projecting it either live or dead. We saw yesterday that as soon as you measure it, it will collapse to one state or the another, which is completely dead or completely alive. This phenomena we call decoherence helps us to understand why it is that quantum phenomena, although they occur at scale of individual atoms or electrons, are not generally seen in macroscopic systems, because macroscopic systems cannot be perfectly isolated from the environment. Now, a quantum computer won't be much like a cat, probably, except that, like a cat, we won't be able to perfectly isolate the quantum computer from the environment. And that will lead to decoherence, because if it is not isolated from the environment, then the noise of the environment will surely introduce errors in quantum computing, which will cause a quantum error to crash. So if we are going to operate one successfully, any one quantum computer successfully, we have to somehow find a way to protect it from the damaging effects of decoherence and any other possible sources of error that could cause the quantum computer to fail. Well, as we know, errors can be a problem even in the classical world. It's not just in the quantum world. So we all have bits that we cherish so much, which we'd like to protect everywhere. It seems though, even in classical computing, there are dragons which are lurking, who delight and tamper with our bits, like viruses. changing their values, but we've learned some ways of protecting ourselves against the dragons in the case of, so in the case of classical information, because I have a bit that I want to protect, I can store backup copies of the bit, and the dragon might come along and flip the value one of those bits. So let's say we had 000 and the dragon makes it 001, but as long as it hasn't had a chance to flip more than one or to flip two of the three bits, we are okay, because we can, let's say, employ a busy weaver like an antivirus who's looking at it, or a file integrity monitoring system that's looking at it, frequently checking to see if the bits all had the same value, and if the weaver finds that one of them has a different value, he flips it back, and we recover the original undamaged encoding state that we have used the principle that by redundantly storing information, we can protect it against errors. Now, we'd like to use the same principle in the case of quantum information, but first it seems like there might be some difficulties. As already noted, we cannot copy. You remember, we cannot copy an unknown quantum state. So we can't make a backup copy of the qubit, a state of a quantum computer in the middle of computation. That just won't work. And furthermore, there are more things that can go wrong with quantum information than classical information. If it's a qubit, let's say it's a qubit, then it is possible that a dragon will open door number 1 and flip the color of the ball from red to green and then close the box again. Now it is tampered with the bit, but instead he could open door number 2 and change the color of the ball and close the box again. So the first type of error is just like a bit flip error that occurs in classical information. The second type is what we call the phase error, and it really has no classical analogy. Now these phase errors are especially problematic because there's another way of thinking about them. A phase error could be caused if the dragon opens door number 1 and instead of flipping the bit from 0 to 1, the dragon just remembers the bit or makes a record of what he saw in memory, and the result of keeping that record will be able to change the value of the qubit when we open door number 2. So he's just remembered, the dragon has not changed the value of the bit when he opened door number 1, but he uses that value to change the value of the bit when he opens door number 2. And that is what is called a phase error. So it has not made any copy, but it is using that. Now, and because it's typically easier to remember a bit than to flip a bit, these phase errors are particularly pervasive and problematic, and we have to prevent them. To resist decoherence and make a quantum computer work, we have to prevent the environment from learning anything about the state of quantum computing during the computation. So we have to keep it isolated in some way, shape or form from the environment, prevent decoherence and prevent errors. Any record left behind will cause the quantum computer to fail. It should be then that if a quantum computation does work, and then after it's over, you ask the quantum computer what just happened, the answer you should get from a quantum computer is, I forgot, I don't remember what happened. Because if it remembers, then there is a problem, then the phase error has happened. And no record should be left behind. The final result of the computation can be published or broadcast, but the state of the computation during the computation must remain a secret. Well, what we need to do then is to store information in a way that environment cannot access it. And the trick is to use entanglement to store the information in a highly entangled state. In a highly entangled state, I can store a qubit in a state of 3 qubits, like we could store a bit in a state of 3 bits and protect against one error. But it works if I use 5 physical qubits. Now, if I store information in 5 physical qubits, to store 1 logical qubit, that can be done in such a way that if the dragon comes along and makes any observation or performs any operation he pleases on one of the 5 qubits, the dragon will learn nothing about the encoded state. That's because the information is encoded in a highly entangled state, and one of these qubits is just like 1 page of our 100-page book that we saw. All the information is in how that one is correlated with the other. So we can have the beaver come along and check those multi-qubit correlations to see if they have been damaged, and reverse the damage without the beaver ever finding out what the actual encoded state is either, and the information can be recovered in its original form. That's what we call quantum error correction. So even in quantum world, it's possible by redundantly encoding information to protect it against the errors, but the information has to be entangled amongst more qubits, and there has to be correlation to take care of that. Now, yesterday moving on to our quantum gates. Yesterday a student asked about, do we have gates like logic gates in classical computers? So the answer was yes, and these are called quantum gates. Now, if you look at classical AND gate, in the classical computing, we have got classical AND gate. How does it work? So here's an example where you take A and B are the inputs to the AND gate, and this is the classical AND gate, and we get C as the output. Now, what happens here is, in the table that you see 2 inputs. The 2 inputs, 0 and 1, A and B. If both of them are 0, the output is 0. That's how AND gate works in classical computing. 0 and 1 gives you 0, 1 and 0, it will be 0. Only 1 and 1 will give you 1. The problem though in quantum is that the above 3 things where the output is 0, in quantum world the information gets destroyed. Now, because the information gets destroyed, it will cause the heat to be evolved, and it will affect the other quantum bits which are right now in superposition, because of the heat, the state of those quantum bits will get altered, creating errors or creating wrong answers. So this type of classical gate cannot be used in quantum computing. This is the reason why classical gates cannot be used in quantum computing. So what we want to use to protect the superposition of qubits, we must use quantum gates. So what is this quantum gate? They are similar to classical gates, but do not have a degenerate output, which means that their original input state can be derived from their output state uniquely. So if you go back, here if you see the output C, now if you see the second row where input A is 0, input B is 1, and the output is 0. If you only knew the output 0, can you confidently say that the input was 0 and 1? A was 0 and B 1. You can never say that, because there are three ways you could have got the output 0. Even in row 1, if the input A was 0, B was 0, still the answer was 0. And in row 3, when the input A was 1 and B was 0, still the output was 0. So by just knowing 0, you cannot find out the previous state what it was in. But in quantum computing, the gates have to be reversible. This means that a deterministic computation can be performed on a quantum computer only and only if it is reversible. And the good news is that in 1973, Charles proved that any deterministic computation can be made reversible. And let's see how these gates work. So, to look at the kind of gates, we have a poly X gate. So there is a poly X gate, there is a poly Y gate, there is a poly Z gate. There are different other gates, but the most majority of them that are getting used is these three gates, and also there is a Hadamard gate. So we'll go and try to understand what this means. The poly X gate is basically acting on a single qubit. Okay, and the direct notation, the way it is written is using the bracket notation. Bracket 0 changes to bracket 1, and bracket 1 changes to bracket 0. In the circuit, it is represented as a X in a box, where the lines that you see before and after the box X, those are nothing but quantum wires. They carry the information. Now, acting on pure states become a classical NOT gate. So 0 can be written in matrix form as a matrix of 2 rows and 1 column, where 1 is at the top, 0 is at the bottom. And a bracket 1 can be written as 0 and 1. Now, for ease of understanding, we write x of 0 is 1 and x of 1 is 0. So basically, poly X gate behaves like a classical NOT gate, because in classical NOT, a 0 switches to 1 and a 1 switches to 0. And same is the poly X gate in quantum computing. Then there is a Hadamard gate. Again, it involves 1 qubit. And this gate is basically what it does is a square root of the NOT gate. This is the most widely used, and the majority of times you will see Hadamard gate is used in quantum computing algorithms, because this is used to put the qubits into superposition. And there is no analogy in the classical system of this gate, because superposition is not a property of classical system. It is represented by H in a box. And the direct notation is bracket of 0 is 1 upon root 2. It's known as the square root of NOT gate. Bracket of 0 plus 1, and bracket of 1 is 1 upon root 2, bracket of 0 minus 1. And when we talk about Hadamard gate, it's 1 upon root 2, 1, 1, 1 minus 1. That's the notation. Right now, you don't need to go deep and understand how this notation comes. That itself is a very complex formula, and it will require a lot of understanding and knowing about the discrete mathematics. But at this point, as far as we are concerned, we should know the direct notations. We should know how it works. There is no classical equivalent to this. We should understand this. There is no classical equivalent to the Hadamard gate, and it is one of the most important gates for quantum computing because of its ability of handling superposition. Now, to understand, let's take an analogy. What does Hadamard do? Now, let's go 1,000 years back when there were no boats or ships, and we had to go from this position to this position. Let's say somewhere from North Africa to Spain, for example. How would one go about it? Because there was no boat here, there were no ships, they couldn't swim. So how would one person go from here to there? So they would basically use this route, go from land all the way here. That's what classical computer does. It lets you go like this all the way using zeros and ones, zeros and ones. This is the way you go. You use AND gate, OR gate, NOR gate, XOR gate, NAND gate, all those gates, and this you take this path. But if you had a boat or if you had a ship, you could directly go over the water from here to the other end. This is actually what the Hadamard gate does. It removes all that complexity of going, and it creates many paths which are superposition states, and that superposition states help you go from here to here through ship, through plane, through boat, and also through land. It gives you all different states. So how an Hadamard gate can be used as a NOT gate? If you put two Hadamard gates in succession, it will behave like a NOT gate. So how does that happen? So we saw that Hadamard of 0 bracket was 1 upon root 2, 0 plus 1. We already saw that equation here at the bottom. And bracket of 1 was 1 upon root 2, 0 minus 1. So we are taking that same equation here. H of 0 is 1 upon root 2, 0 plus 1, which is 1 upon root 2, 0 plus 1 upon root 2, 1. And H of 1 is 1 upon root 2, 0 minus 1, which is 1 upon root 2, 0 minus 1 upon root 2, 1. Now, this is a balanced equation for a superposition, 50% yes and 50% no. Now, if we apply an hammered gate to the first result, which is 1 upon root 2, 0 plus 1 upon root 2, 1, the first one, it will give us 1 upon root 2, and then replace the 0 again by 1 upon root 2, 0 plus 1, plus 1 upon root 2, and then replace the 1 by 1 upon root 2, 0 minus 1, and you will see that it will turn to 0. And then you again apply the hammered gate to the second position, and you will see by the same kind of calculation, you will get 1. So basically what this is saying is that if you apply two Hadamard gates, one after another, it can be used just like a NOT gate. So it's a very, very powerful gate. Then there's a poly Y gate. Again, it acts on a single qubit. But you see the direct notation. 0 becomes I of 1 and 1 becomes I of 0. The circuit representation is a Y box. So this is also turning a 0 into 1 and a 1 into 0, but This is a NOT gate with I multiple. Okay, and I could be any number. So again, there is no classical equivalent to this gate because there is no I in the classical system. And then there is a poly Z gate, or Z as they say. Again, it acts on a single qubit. What this does is, this gate is used to flip the sign of the second entangled state. So if I open box number 1 on Earth, door number 1 on Earth, and it has a red ball in it, and my friend opens door number 1 on Mars, and that has to happen, it has to have a red ball in it because of the correlation and entanglement. But using this gate, I can change that red to a green in Mars, and that is flipping the sign of second entangled state. So 0 to 0, 1 to -1. It's only the second state which I'm changing, not the first state. So this is again a circuit representation of poly Z gate. Just going back to poly X gate, which is equivalent of NOT gate that we saw. So if you go to poly X gate, we saw that poly X gate was 0 to 1, 1 to 0, and that is equivalent of our classical NOT gate. In classical NOT gate, if A is 0, the output is A bar is 1, and if A is 1, A bar is 0. Similarly with poly X gate, there is no difference. So poly X gate is equivalent of the NOT gate. Two hammerhead gates in succession can also behave like a NOT gate. And for poly Y, poly Z, and hammerhead, there is nothing which is similar in classic computation. And these are the powers of quantum mechanics. These logic gates are the power of quantum mechanics. There is also a controlled gate. What is a controlled gate? These gates operate on 2 qubits or more qubits. You can have 2 or 3 qubits. But a controlled NOT gate is a 2 qubit. It operates on 2 qubits, and it's also called a CN gate. So here, one line is called the control line, and the other line is where actually the bit is getting passed, which is the input and the output. Now, if the bit on the control line is 1, it inverts the bit on the target line from 0 to 1 or 1 to 0. So let's look at the input and output table on the right. If you see A is 0, B is 0, there's no change. If you see A is 0 and B is 1, B is the control line, and what we say, if the bit on the control line is 1, then it will flip the bit on the target line. So because B is 1, it will flip the 0 of A to 1. This is the second row that we are saying. Third row, B is 0, so it is not flipping the A gate. It's 1 is still 1. And in the fourth, where B is 1, it
हॅलो सर, तुमचा आवाज येत नाहीये.
Yes, ma'am. I was disconnected.
या सर.
Were we here on this screen?
Yes, sir.
Okay. So I'll just go through the screen again. So a controlled NOT gate is one which operates on 2 qubits, and if the control bit is 1, then the other bit changes or flips itself from 0 to 1 or 1 to 0. So if you look at the table on the right, row 1, where A is 0, B is 0, so the output is also 0 and 0. But in the second row, where the control bit is 1, B is 1, you will see that the output A changes from A dash is changing from 0 to 1. And in the third row, where control bit is 0, A remains same. And in the fourth row, where control bit is 1, A changes from 1 to 0. Look at it and compare and contrast with the classical computing. You will see that this gate has a similar behavior to the XOR gate with some extra information to make it reversible. Then there's an example operation. How do you multiply by 2? So we can build a reversible logic circuit to calculate the multiplication of by 2 using a CN gate. If you arrange the gates in the following manner, you will see that, if you do the calculation, if you know how to do logic gate calculations, you will see that how we can do multiplication by 2 by adding a hammer and gate. And then there is a controlled NOT gate. It's a CCN gate. Now this gate operates on 3 qubits, and it's called a CCN gate. If and only if the bits on both the control lines B and C are 1, then the target bit is reversed or inverted, otherwise it is not. So look at the table on the right. If you see row number 2, control C is 1, but because B is 0, A is not reversed. A is 0 and A dash is 0. Look at row number 4. You will see 0, 1, 1 as the input. Now here you see B and C are 1. So both control gates are 1. Because of that, you see A dash becomes 1. From 0, it gets inverted to 1. And similarly, in the last row, from 1, A gets converted to 0 because both the control bits are 1. So this is a CCN gate, or controlled NOT gate. And a universal quantum computer, so the CCN gate has been shown to be a universally reversible logic gate, and it can be used as a NAND gate also. You can always reverse back because of 2 control gates. You always know what the input was. So when our target input is 1, our target output is a result of NAND of B and C, and not AND of B and C. Shor's algorithm, so we know there's Shor's algorithm, there's Grover's algorithm, different kinds of algorithms. I thought that let's just go briefly touch upon the Shor's algorithm. It's very complicated for us to understand because of the nature, but let us try to see how Shor thought of doing, how a quantum algorithm got evolved for prime factoring of a large prime number. And this again is, dependent on many other kind of phenomena like modular arithmetic and quantum parallelism and Fourier transformation. That requires a deep study of quantum algorithms. But just to touch base on how quantum algorithm works, and how Peter Shor did this. So one of the results from number theory, which we all know, function of A is x raised to A mod n. It's a periodic function. What do you mean by periodic function? So let's say I choose a number as 15, and I choose my x as 7, and I do x raised to A mod n. So you will see 7, 0 mod 15 is 1, then 7, then 4, then 13. Again, when you come to 7 raised to 4 mod 15, it will again become 1, 7, 4, 13. So this is a periodic function. That's what in mathematics it's called a periodic function. Now, if we take any periodic function and we chose a number like 15 and x is 7. Remember, this x is 7, n is 15. So Shore's algorithm, what it did is, it says that choose an integer q such that n square is less than q and which is less than 2n square. So n is 15, remember, n square is 225. So we need to pick up a number q which is greater than 225 and it is less than 2n square. Okay, what is 2n square? That is 225 into 2, 450. It should be less than 450. So here let's pick an example, 256, which is between 225 and 450. And then we choose a random integer x such that the greatest common divisor of x and n is 1. Now n is 15. So we pick up, let's say, 7. Because 7, we can say, is the greatest, we can say 7 is the number here. And let's create two quantum registers. And they are in entangled state. Which means that when you measure the input or observe the input, or the input register collapses, the output register should also collapse to 0 or 1. Now the condition here is that the input register must contain enough qubits to represent the number as large as q minus 1. Remember, q was 256. So we should have the input register with so many qubits that it should at least be able to house 255 as the number, which is, 8 qubits can house 256 numbers. We know 2 raised to 8. So we need 8 qubits. An output register must contain enough bits to represent numbers as large as n minus 1. N is 15. So we should be able to house at least 14 numbers. So we need 4 qubits because 2 raised to 4 is 16. So 4 qubits can house the output. Now load the input register with an equally weighted superposition of all integers from 0 to q minus 1. So from 0 to 255, we load the input register and load all the output registers with 0. Okay, so output registers is 0. And the comma here is saying that the registers are in entangled state. Changing one of the states or collapsing one of the states will collapse the output register also. Collapsing input will collapse the output. Now we apply the transformation xa to mod n to each number in the input register. So let's take number 0. So 7 raised to 0 mod 15 is 1. Then take number 1 and we will go this, for each number in the input register up to 255 we will go like that, and you will see that the output register will get a periodic reply 17413, 17413 and so on. Now let's take a measurement on the output register. As soon as you take a measurement, we already saw in the phenomena of superposition, as soon as we take the measurement, this will collapse the superposition to represent just one of the result of the transformation. Let's call it C. So our output register will collapse to represent one of the following. It will either be 1, 4, 7 or 30. Now for sake of example, let's say that the output collapsed to 1. From here, since the two registers are entangled, measuring the output register will partially have an effect of collapsing the input register also into an equal superposition of each state between 0 and q minus 1 that yielded the output C. What was the output C? 1, which we took, the value of the collapsed output register. Now since the output register collapsed to 1, the input register will collapse to 0, 4, 8, 12, only these possibilities. Why? Because which output register collapsed to 1? It was the input register 0, input register 4, input register 8. So as soon as the output got collapsed to 1, the input also got collapsed to only the ones that can yield output 1. This is entanglement. So the probabilities in this case are 1 to the root 64, since our register is now is an equal superposition of these 64 states, 0 to 252. What are the 64 states? 0, 4, 8, 12, 16, that kind of 64 states. And now to this, we apply the quantum Fourier transform. We will not go into detail of quantum Fourier, but just understand this is an algorithm that you directly call. What do you pass to this algorithm? And what does it do? It takes a state A and transforms it into a state which is given by 1 upon root q. And it sums up from output C 0 to q minus 1 and bracket C multiplied by e raised to 2 pi ac slash q. We don't have to know the intrinsic. All we need to know is that it will take a state and it will transform it into a quantum Fourier state. So basically, we know that A is the set of all the values that yielded 1, which was 0, 4, 8, all those things. So 1 to the root 256, 0 to 255. The final state of the input register will be 1 root 64 and then sum of 1 root 256, C equal to 0 to 255, bracket C. It is nothing but just putting values in this. We know the value of Q, we know the value of Q, C, we know the value of A, C, Q. That's all. We've just put these values here. That's all we have done. And the QFT will essentially peak the probability amplitudes at integer multiples of Q by 4. So we no longer have an equal superposition of states, which we started with. We started with this equal superposition of states, 1 upon 64, 0, 1 upon 64, 4, 1 upon 64. But after doing the Fourier transformation, the states that came out were 0, 64, 128, 192. And how did that come out? Using quantum mechanics, using the quantum Fourier transformation, the probability amplitude of the above states are higher than the other states in our register, because they were all in superposition states. So quantum found out that these states have higher amplitude than any other. So we measure the register and it will collapse with high probability to one of these multiples of 64. Let's say it collapses to P. Now with our knowledge of Q and P, there are methods of calculating the period. It's a continuous function. Now once we get the period, the factors of n can be determined by taking following equation, and that's how we will come with two numbers, 5 and 3. So we have successfully factored 15, but it doesn't end here. The QFT comes up short and reveals the wrong period. Sometimes QFT will not always come out with the right answer. Remember, it's the probabilities of answers that you get together. So this probability is actually dependent on our choice of Q. The larger the Q, the higher the probability of finding the correct probability. The more number of superpositions, the more the probability of finding the correct Q. So the period of the series ends up being odd. If either of these cases occur, then all we need to do is we go back to the beginning and pick a new X here. Remember, we picked 7. Now we pick some other random integer where the greatest common divisor of that number and 15 is 1. We can pick 8 and then again do this whole thing, and this is the way Shor's algorithm factors the prime numbers. The beauty of this is that a 193-digit number, the factors can be found, and it has actually been run on only 15-digit number till now. And it has shown some great promise in quantum mechanics. So, research is going on, and this is how Shor's algorithm works. So, to conclude what we know about quantum mechanics, we know what we went through we understood the Schrodinger's cat experiment, how a thing or any subatomic particle can be in superposition state, both dead and alive at the same time, an example of cat, if properly isolated from the environment and there is no decoherence. We saw that a photon or an electron or subatomic particle can be in both the states at the same time. It can behave like a particle and it can behave like a wave at the same time. But if an observer is kept, it suddenly collapses to a particle. Whenever two qubits or two states exist in an entangled mode, they are correlated with each other such that looking at state of one qubit can make you understand the state of other qubit, no matter how far it is in the universe or galaxy. The measurement collapses the state. We looked at decoherence, which is removing the noise of the environment, because if there is even the slightest of heat or noise or the waveform of noise, then the superposition in the qubit will get disturbed and errors will be incurred. So those are called quantum errors, and to remove those quantum errors, we need decoherence. We saw the quantum error correction, how that happens. Though we cannot make a copy of a quantum bit while in the process of computation, we can definitely create copies, after the computation and before the computation. We saw that there are good amount of algorithms. We touched on Grover's algorithm yesterday, and we saw the Shor's algorithm today, Peter Shor's algorithm to finding prime factors. We touched on the computational complexity yesterday, because the computational complexity of quantum was square root of n, while of classic it was n factorial. We saw that prime factoring is a major formula that gets used in the security or the cryptography, where public and private keys, to generate those kind of keys, we use this phenomena of RSA uses the phenomena of cryptography. So quantum and prime factoring of Shor's algorithm has a great use there. But then it also raises a question: if Shor's algorithm becomes so fast, then we would be able to break today's security within 0.1 second. Then what are the next security? What is quantum security? That opens another area of research now. How will quantum security work? And we saw that information theory, everything can be represented as a quantum information. And when it is in a quantum information, it is basically in an entangled state. Just by reading 1 or 2 pages of the book, you cannot understand the 1 or 2 pages of the book. You have to read simultaneously many pages of the book correlated with each other, and only then you can decode and make sense of what's there in the quantum book. So, to sum it all up, I don't know about you, but I'm actually in the state of understanding and not understanding. It is a very superposition state that my brain has gone in last 2 days. And this is how it looks. The first time I read about quantum mechanics, and no matter how many times I keep on reading about quantum mechanics, it still makes no sense to me. And at the same time, it does make sense to me. So that's what quantum mechanics is all about. I I hope that in these last 2 days, I've been able to at least give a drop from the ocean of quantum mechanics to at least start the brain's thinking in that direction. I know it's very complex. I don't even, you know, I don't even assume or expect anyone to, just grasp it in 1 day or 2 day. Trust me, I've gone over it hundreds of times before I could bring it to the level which is still, I know, difficult to understand, but I brought it down to a very, very simple level so that I could keep it in front of you in a way that whatever you can grasp from it. So that's it from quantum mechanics. Thank you for being such a patient spectator and an audience. I give it back to ma'am and Vijay sir. Over to you. If anybody has any questions, open for that.
व्हिडिओ सुरू करतो. Hello students, do you want to ask any question? Yeah. Yes. Gidwani, you may ask the question instead of sending the message.
Hello.
Hello,
Yeah,
Husky.
hi, Devil.
So,
Hi, Devil.
queue between two quantum computers, since we can't stop them, and they are also vulnerable to weather conditions.
That's a very interesting question. Actually, two quantum computers, there are certain gates that are available. And you can directly interact a pair of qubits, but when we are talking of sending it to another quantum computer, you can do it through entanglement, just like what I said about, you are opening a box here on Earth, and then there is an entangled qubit, but that qubit, when it was made, these two qubits, right? If a qubit, some is made with a certain property, and both of those qubits have a certain property, then a qubit in one quantum computer can definitely talk to qubit in the second quantum computer, as long as they are entangled. It is just like electrons in the universe, or photons in the universe, or two subatomic particles in the universe. Can a subatomic particle in one universe talk to subatomic particle in another universe? We talk about transportation, right? We talk about, in spiritual world, we talk about if you have connection to souls, you can talk between planets. If there is a soul on moon and there is a soul here, the souls can communicate because they are entangled. Similarly, if you have entangled qubits and they are in different quantum systems, still they can communicate.
But even for entanglement, like you will use one extra qubit and then you will entangle it, and then you have to also send the entangled qubit to the other computer for it.
No, so yeah, you are not actually sending a qubit. It's a qubit that is already there. So it's not physically, you are not sending anything. So that's where, quantum differs. Quantum, we are talking about subatomic particles, right? Subatomic particles, they are like, we need to understand what quantum machine is made up of. A quantum machine is made up of certain things like quantum wires. Now, what is a quantum wire? And how long does a qubit stay in keeps a certain value? It doesn't last for long. It only lasts for some milli or nanoseconds. As soon as it gets a value, it loses the value within nanoseconds because of the state of qubit, which is continuously changing. So similarly, It is not like you are, well, you can encode a qubit in such a way. You don't need a third qubit, but you can encode a qubit in such a way that no matter where that qubit goes, that qubit will always be entangled to this qubit. So you have two qubits which you have made in a quantum system, and through the quantum wires, even if that qubit travels to any other quantum machine on the network, if it carries the property of entanglement along with it, then no matter where it is and in which quantum machine it is, as soon as you change something here, it is going to get changed there. And that's because that is how universe works. That's how quantum mechanics works. And that's the weirdness of it. If you try to reason how, there is no how. It's just the nature of the universe is such that something happening here. For example, if there is a snowfall in North India, we do get certain rain or winds even in Maharashtra, right? And we come to know there was some hailstorm in Jammu, because of which there is some rainfall happening in Maharashtra. How does that happen? Now, if you say that because we sent something from there to here, no, we didn't send anything from there to here. It's just the way universe is. Universe is designed to work in a certain way, and quantum mechanics is about leveraging those weirdness. So how it happens, nobody will ever come to know. But it will happen. Yes, you make two qubits, entangle them, and then anywhere it goes in the universe, any change happens here will automatically have an effect on that qubit.
Okay, sir. The problem is also that when we send, we have to make sure like we don't keep a copy with ourselves, or like that automatically be handled.
You actually cannot copy a qubit in a state. So when there is position, you cannot copy it. But after it has collapsed to a 0 or 1, which means once you have measured it, at that point, yes, you can make a copy of that qubit. But if you make a copy of that qubit copy will also be entangled. You can make a copy. Remember, it's not that you cannot make a copy. You cannot make a copy when it is in computation stage, because the moment you try to make the copy, the superposition makes it change its, whatever state it is in. The state is always changing, right? In superposition, sometimes it is 60% 0, 40% 1. Sometimes it is 62% 0, 38% 1. It's continuously changing. So that's why you cannot make a copy. But once it has become 0 or 1, you can make a copy. And that's when you make a copy, make an entanglement and send it in.
Sir, in traditional computer, there is assembly language to control the actions of quantum, means actions of processors. For quantum processor, is there any assembly language, or is there any assembly level language?
Right now, there is nothing which is open to public. Right now, the only language, you can use the Qiskit from IBM, and you can code over quantum computer. You can do programming over it, but nothing open to public where you can actually change something inside a quantum computer. It's not that simple to do that.
Sir, can the quantum computer will be used for gaming, like applications like high level graphic designing or that type of things?
It will be. The reason it will be used is because it can solve these kind of certain. I told you about, I don't know if yesterday you were there, we saw that example of quantum chess. Now today, what we see about the chess game, and we see artificial intelligence. We saw Dr. Watson winning. IBM's Dr. Watson machine won the game Deep Blue. It was named Deep Blue. In 1997 or 2000, sometimes it won the game against Gary. So quantum chess is something which will change the way chess is played. It can make decisions like whatever took 2 steps to do using quantum superposition, you can do it in 1 step. We saw that yesterday. So the probability of winning the game increases, which means that there will be quantum games, and those quantum games will favor more to the quantum machine. It will be difficult to beat those quantum machines, because what it will take for a human mind to understand and play its next step, quantum will be able to superposition all the upcoming stages and bring out all the best stage with more than 85% probability of winning, which a human, without knowing the inputs and outputs entanglement, can only win up to 75%. But the answer is yes, there, it will be used for games, but that is once it becomes, mainstream, and there's a lot of time to reach there, because there are so many challenges that we still need to overcome, even to make it a workable quantum computer where it can solve like the prime numbers thing. If I want to solve a prime number, 500 digit prime number factors, if I want to find that, that is a bigger problem today to solve than playing games. So can it be done? Yes. But will such a sophisticated thing be used for playing games? I don't think so, because it will be like sitting in an aeroplane and 400 people, instead of flying, if the aeroplane only takes you on runway, taxis here and there, and then takes you to another gate and drops you. It will be like aeroplane doing a job of a bus. Even a bus could do that. You don't need an aeroplane for that. So similarly, quantum computer, if it is used to play certain games, then it doesn't make sense. That's what I feel at this moment. But yeah, what future holds, I don't know. It's very, very new for me also.
Sir, I am talking about not the simple games. I am talking about high level graphics, means high level graphics, high level images, like Meta.
Yeah. For Meta and all, maybe we will have this quantum gaming, which is again an upcoming stream in quantum computing. But at this moment, too early to say, because those games will be written in a totally different. Again, we need to prepare algorithms for those games. But yes, one day will come when definitely you will see games. Not in near future. I don't see it in near future. Though they did have a theory of quantum chess, right, which we spoke about yesterday. So there are people who are building something, but when it will become mainstream, really don't know.
Means today we can't use the high level languages on the quantum computer. Means
Quantum
like
computer
Python.
has its own languages. So if you want to know more about it, just go to Google and type IBM QuizKit. And in IBM QuizKit, you get the complete kit for quantum information system. Everything, whatever you need get the platform for programming, you get the editor, you get everything in that.
Okay. Anybody wants to ask the question? Yes, from student side. Yes. So shall we conclude the session, students? Yes, Sakshi, Kajal, Krutik.
No, ma'am.
Do you want to ask any question? Okay. Sir, shall we conclude the session then?
Sure, ma'am. Thank you. Thank you. It was wonderful.
Okay. Okay. So I will ask Nitanshu Shane for the vote of thanks.
Yes, thank you, ma'am. Good afternoon to one and all present here. I, Nitanshu Shahane from BE Computer Department, feel it's a great honor to have been asked to offer a vote of thanks on this occasion. On behalf of everyone present here, I express my gratitude to Dr. Rajeev Papneja for conducting a session on quantum computing. I would also like to thank our HOD sir, Dr. M.U. Karat, Shubhangi Harkunde ma'am, Vijay More sir, and all the other staff members for their encouragement and guidance. And thank you everyone for being present here today. Thank you, sir.
Thank you, Nitanshu. Thank you so much.
Thank you, sir, for your valuable time, valuable guidance to the students of our BE.
Thank you, ma'am. Thank you. Always a pleasure.
Yes. Welcome, sir. Okay, here I declare that the session ends here. Okay, and all the students give the feedback. I will send a link to you and Google form also. Okay, so as you will be in the loop of the feedback and Google form for the question answers, please respond it as early as possible. Okay, you may leave
Thank
the
you.
meeting.
Thank you. Thank you.
Yes, sir. Thank you.
Thank you.